Hello all, welcome to section 1.5, solutions to linear systems. Okay, so we started this entire term talking about solving a linear system like so. We introduced notation just to say that if A is this matrix that picks up the coefficients of these equations, and B is a vector that collects the numbers on the right-hand side here, and X is this variable vector, then star, our system of linear equations, can be rewritten or is equivalent to the matrix equation AX is equal to B. So what we want to do is study the solutions to these equations, and we'll start with the special case where B is the zero vector. So the equation AX is equal to 0 is called a homogeneous equation because what it's being equal to is the zero vector 0, 0, 0. Don't ask me why that's homogeneous, but that's where it is. Yeah, it has the unusual property that there's sort of a solution to this equation already built in. So every time you throw in X is also equal to the zero vector, no matter what matrix we chose here for A, this equation is satisfied. So every homogeneous equation has at least one solution, this trivial solution. And recall from section 1.2, I think it was, in general, what we can say about a matrix equation, AX is equal to B, it either has no solution at all, exactly one solution, or infinitely many. Those are the three boxes that each matrix equation comes in. So for homogeneous equations, we can already eliminate no solution. Definitely it has one solution, it could have infinitely many, but definitely it has one. So we've reduced our possibilities from 3 to 2, which is significant. Right, so we call this like boring solution to the homogeneous equation the trivial solution. But right. So there's always the trivial solution to any homogeneous equation. There could be other solutions, non-zero solutions to this homogeneous equation. Those are called non-trivial solutions. Boom, to our homogeneous equation. Homogeneous? I think both pronunciations are acceptable. Anyway. But we just saw there's either exactly one solution to this homogeneous equation or infinitely many. So if we get a single non-trivial solution to this homogeneous equation, then we know there can't be no solution, can't be exactly one, because we've got the trivial solution and some non-trivial solution. So our only possibility left is infinitely many. So as soon as we get a single non-trivial solution to our homogeneous equation, AX is equal to the zero vector, then there must be at least 2 solutions in total, and so there must be infinitely many solutions to our homogeneous equation AX is equal to 0. So again, previously we've seen that infinitely many solutions corresponds to having a free variable, and so finally we can give the punchline to all this, which says what? So the homogeneous equation AX is equal to 0 has a non-trivial solution. If and only if there's a free variable in the corresponding linear system. Corresponding linear system has a free variable. Okay, now it's probably time, or maybe we're overdue for an example to just see what's going on actually. So let's determine if the following homogeneous linear system has a non-trivial solution, and if it does, give an example of one of them. And what we should see is that either there's only trivial solutions, or we get some infinite family of non-trivial solutions. So we'll do the same thing we've always done, which is row reduce. Right? We've got this nice matrix. So our solution here. We've got the matrix 2, -1, 3, 0, 4, 3, 11, 0, 1, -2, 0, 0. And what should we do? Let's swap row 1 and row 3 to get that that 1 in the top slot. So 1, -2, 0, 0, 4, 3, 11, 0, 2, -1, 3, 0. Okay, and next, yeah, let's use the 1 in the top left to get zeros beneath it. So we'll do row 2 minus 4 row 1. We'll do row 3 minus 2 row 1. It's going to give us 1, -2, 0, 0. And then 0, 11, 11, 0. And then 0, 3, 3, 0. Okay. So then let's do, yeah, row 3 minus 3 11ths row 2, which looks terrible. But what's going to happen is we're going to get what? 3 minus 3 and then 3 minus 3. So our first row isn't changing at all still. Our second row isn't changing. And our third row is all zeros now. Oh, need a little more space. Boom. There we go. Right, so now we can go, let's scale the second row by 1/11. 1, -2, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay, and then we'll do row 1 plus 2 row 2 to get 1, 0, 2, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay, and now we're in reduced row echelon. So what can we say? So this means what? Our equivalent system, or our original system at least, was equivalent to the system x1 plus 2x3 is equal to 0, and x2 plus x3 is equal to 0. And so we're getting x1 is equal to -2x3, we're getting x2 is equal to -x3, and x3 is free. Okay, so if x is a solution, x1, x2, x3, so this is just going to be equal to -2x3, -x3, and x3. Or if you pull out a common factor of x3, we just get -2, -1, 1. And so sure enough, we do get infinitely many non-trivial solutions to our homogeneous equation. Any multiple of this vector gives you a solution. Right, and they're all non-trivial except for when x3 here is the number is 0. Okay, so then, so what? So what were we asked to do again? Always a good question. Determine if it has non-trivial solution. Yes, so the answer is yep. Yep. Our system has non-trivial solutions. Oops, a little messy. Solutions. And then pick your favorite example. I'm going to pick the absolute boringest one, -2, -1, 1. It's a non-trivial solution. Okay. Good. And then I almost asked for questions again because I've not yet internalized that you're elsewhere. But okay, fine. Yeah, let's go back to, we'll do another example. And this time all we've changed is, instead of having everything equal to 0 for a homogeneous linear system, we've swapped out some of these numbers. So it's the moment we change one of these even to be non-zero, the whole thing fails to be homogeneous. So now we've got a non-homogeneous situation. So there isn't, so in the general non-homogeneous situation, there's no longer any reason to think that any solutions exist. We don't have this this trivial solution situation. All no bets are off. All bets are off. All bets are off. We could have no solution, one solution, infinitely many. Okay, so then so you might be asking, well, what are we expecting to see here, David? And you'll see, trust me, we're working after something. You will see a thing at the end, I promise. Meanwhile, all we're going to do is try to solve this linear system the same way we always do, row reduction. Okay. So again, check out that this part has not changed at all. All we've changed is instead of being all zeros, we've got some non-zero terms in our vector B. Okay, but then our methods actually won't change at all, and even the order of operations isn't going to change. So our matrix that we're interested in is now 2, -1, 3, 0. That one, even that row is the same. 3, 4, 11, 10, 1, -2, 0, -3. So we're going to repeat the exact same operations, just keeping track of what happens to this rightmost column. Okay, so let's swap row 1, 3 again. So 1, -2, 0, -3, 4, 3, 11, 10, 2, -1, 3, 0. Okay, again, we'll do what? Row 2 -4, row 1, row 3 -2, row 1. So we get 1, -2, 0, -3, 0, 11, 11, 22, 0, 3, 3, 6. Okay, yeah, it looks like I've done things in slightly different order. That's fine. So let's do 1/11 of row 2, and we'll do 1/3 of row 3. So 1, -2, 0, -3 still. 0, 1, 1, 2. Oh yeah, this is going to be a little bit 0, 0, 1, 1, 2. Really? Yeah. All right. And so we get is what we want, row 3 minus row 2. I guess that makes sense. Okay, 1, -2, 0, -3. 0, 1, 1, 2, all zeros. And then what? Row 1 plus 2, row 2. Finally, to get us back to 1, 0, 2, 1, 0, 1, 1, 2. Yeah, 0, 0, 0, 0. Okay, okay. So we get now what? The system x1 plus 2x3 is equal to 1. x2 plus x3 is equal to 2. And x3 is, yeah. Okay, so yeah, that's right. x1 is just 1 minus 2x3. x2 is 2 minus x3. And x3 is free still. And so if x is a solution, so x1, x2, x3, it has to look like 1 minus 2x3, 2 minus x3, and x3. And we can rewrite this as what? 1, 2, 0 plus x3, -2, -1, 1. Okay. Okay. So we've done this a million times now. We're mostly okay with how this all goes, maybe, hopefully, either way. The thing you're supposed to notice is this looks awfully familiar. Hopefully this looks very familiar. This is exactly what we had for our solution a moment ago. So the thing we're supposed to notice is the solution to the non-homogeneous equation includes, a single vector and the entire homogeneous solution. So it isn't like they're closely related. It's saying anytime you want a solution to the non-homogeneous equation, it should look like a single vector plus some solution to the homogeneous one. So they're just taking every solution to the homogeneous equation and moving over a little bit, moving over by this vector. Okay, so maybe let's write down that observation. So observe. Yeah. The non-homogeneous solution homogeneous solution is identical to the homogeneous solution. Plus a single vector. In this case, 1, 2, 0. Okay, and this was not carefully crafted. This is true in general. Before we get to the statement of that theorem, let's do something unusual and go to GeoGebra to see if we can visualize what's happening here. Unless I've closed the window that I wanted. No, okay, one sec. Let's change this share here. Okay, boom. So now we should be able to see GeoGebra. Yeah, so let's put up the original 3 equations that we had. So each of these equations cuts out a plane in space, and if the planes overlap in a line like this, that line common to all 3, that's your solution set. This is the line that we carved out by looking at all multiples of the vector -2, -1, 1 in our first example. Okay, and then so we can get rid of these and do the same thing with the non-homogeneous situation where we had 10. Oops, this is in the wrong order. It doesn't matter. The order doesn't matter. Okay, or we had 0, 10, -3. If we post those, you see, okay, well, we're getting the same line, but like shifted over. And if you don't like seeing a bunch of planes, I don't blame you. Oh, we're buffering. Here we go. Yeah, the same situation is illustrated here without all the planes. So in our, oh, what's happening? We're buffering again. Technology, ladies and gentlemen. Giveth or taketh away. Do y'all like my t-shirt? Huckle Cat, classic Richard Scarry. Okay, well, maybe I'll try to show what's happening here. Here we see a line to the origin. That is our our homogeneous solution. It contains a 0 vector, right? 0, 0, 0 is always a solution. The non-homogeneous is just that exact same line shifted over by the vector 1, 2, 0 right here. I don't think it's coming back, but maybe. Tempted to just redo the video where things are working, but not that attempted. Okay, well, maybe let's go back here and take a look at it again, make sure that we can see everything. We can show all 3. Boom, boom, boom. And now we can see the intersection of all those blue planes is right here. That's one solution set, giving you a line to the origin. The intersection of all the orange planes is right there, giving another solution set, again, just shifted by this vector 1, 2, 0. Now it's harder to see that vector than it would be in these lines case that isn't loading because life is terrible. But that's the whole point. Just that geometrically what's happening is you've got your homogeneous solution set. If you shift it over, you're going to get these solution sets to various non-homogeneous situations. Okay, and I've officially given up on that GeoGebra thing ever loading again. So let's go back to our notes. Boom. There it is. Okay, back to our notes. Let's write up this theorem that says this observation that we made here is always true. It's always the case that the homogeneous solution is buried inside of your non-homogeneous solution. Boom. Oops, theorem 6. Okay. Suppose AX is equal to B is consistent for a specific vector B, and that P is a solution to this system. Pardon me, this system. Then every solution W to this equation, our non-homogeneous equation, looks like P plus some non-homogeneous or some homogeneous solution. Right, every solution to this equation is just P plus something else to it. So we can generate, from one solution, we can generate them all from solutions to the homogeneous equation. Or the other way to think about it, this is that every solution contains sort of a kernel of all of the homogeneous solutions as well. And the proof idea is actually really cute, in as much as math can be cute. I won't give you all the details. The details you can find in the textbook, but look, if we apply our matrix A to W, what's going to happen? This is A times P plus VH. VH, the substrate is supposed to be like homogeneous. It's supposed to remind you that V is a homogeneous solution. So we know that matrix multiplication behaves the way we think it ought to. It distributes. We know exactly what AP is equal to. We assumed that it was a solution to A2X is equal to B. So we know this is B. And we know what AVH is. This is a solution to the homogeneous equation. So we know that whole thing is just equal to the zero factor. So it is equal to B. Boom. Okay. And then all the fun details you can see the book for, but that's basically it. Okay, let's do another example. Okay, so let's let A be this 3x5 matrix. We want to find all solutions to both the homogeneous equation and the non-homogeneous equation. And so if we didn't have this theorem, we'd run through the solution to this one, we'd run through a solution to that one, we'd have to row reduce the matrix 2 times. All we're going to do now, though, is solve this general equation and then seek out the homogeneous part and say, okay, well, it should be some single vector by itself, and everything else, everything with the free variables attached to it, those are your homogeneous solutions. So we've halved our workload. Okay, and if you're not sure what I mean by that, I'll show you right now. Let's row reduce this matrix. Okay, we've got 1, 1, 2, 3, -1, 1, 1, 3, 5, -3, 2, 2, 7, 12, 7. And the first thing we'll do is the natural one. We'll do row 2 minus row 1. We'll do row 3 minus 2 row 1. So 1, 1, 2, 3, -1, 0, 0, 1, 2, 0, 0, 1, 2. I'm sorry. That's why I'm confused. I forgot about R. All right, let's do this over again. Oh wait, no. There we go. All we need to do is add one column here. 3, 0, -1. Okay, and now we want row 2 minus row 1, row 3 minus 2 row 1. So 1, 1, 2, 3, -1, 3, 0, 0, 1, 2, -2, -3. And then 0, 0, 3, 6, -5, -7. Okay, so then let's try and kill that 3 there. So we'll do row 3 minus 3 row 2. So our first row hasn't changed. Second row hasn't changed. Row 3 is changing. 0, 0, 1, 2. Okay. Now we've got our leading ones, so let's use them to do what? Let's use this one to kill off those above it. So we want row 2 plus 2 row 3, and we want row 1 plus row 3. 0, 0, 0, 0, 1, 2. That hasn't changed. 0, 0, 1, 2, 0, 1, and then 1, 1, 2, 3, 0, 5. Okay, now we use this 1 to get rid of that 2. We'll be all set. So we want row 1 minus 2 row 2. So 1, 1, 0, -1, 0, 3, 0, 0, 1, 2, 0, 1. Sorry, that doesn't look like a 0, but it should be. Okay, and then 0, 0, 0, 0, 1, 2. Okay, reduced row echelon. What have we got? This is saying what? x1 plus x2 minus x4 is equal to 3. We've got x3 plus 2x4 is equal to 1. We've got x4 is equal to 2, or sorry, x5 is equal to 2. So which is leaving what? Yeah, okay, so x1 is minus x2 plus x4 plus 3. x2 is free. X3 is minus 2x4 plus 1. x4 is free. And x5 is 2. Okay, so then if x is a solution, then our vector x, x1, x2, x3, x4, x5 is equal to what? Minus x2 plus x4 plus 3. X2 is going to hang out. X3 is minus 2x4 plus 1. X4 is going to hang out, and x5 is 2. So this looks like everything with an x2 in it is coming from -1, 1, 0, 0, 0. Everything with an x4 is where there's a 1 there, there's none there, there's -2, and there's 1 and 0. And then what are the constant terms? You've got a 3, no constant, a 1, no constant, and 2. 3, 0, 1, 0, 2. Okay, so according to this theorem, here is the single vector, and here's an arbitrary homogeneous solution. So for every value of x2 and x4, this thing is giving us a solution to the homogeneous equation. So this is a solution. This is a complete solution to, ax is equal to whatever it was equal to, 3, 0, 1. And what? And what? And s -1, 1, 0, 0, 0 plus t times 1, 0, -2, 1, 0 is a complete solution to the homogeneous equation, the x is equal to 0, where s and t are any real numbers. Right, it wasn't important that they were the second and fourth slot here. They just needed to be some real numbers. No matter which ones you choose, that gives you a new solution to this homogeneous equation. Okay. I think that's all I had planned for section 1.5. I'll see you all next time. Take care, everybody.